Okay, so now that we understand the difference between the different types of prediction formulas we can use for regression, let's go ahead and look at how we test the model. So the first thing that we said is, remember, regression is all about a hypothetical model. We're not actually measuring a person's Y value all of the time. We're using X and Y data that we collected at some point, and we're trying to estimate or guess what a person's Y value would be based off of knowing an X predictor value today. And so when we determine how good a model is, this is basically telling us how good is that line of best fit. Is it even good at predicting that Y variable of interest? And so the model may not necessarily be good at estimating the Y. And in that particular case, do we really even want to use the line of best fit? And so we need to think about that. And so we have to be able to test the model, which is giving us the answer to the question about whether the line of best fit is a good line and can accurately predict the unknown Y value of interest in our given research question. And so we're going to go through that process here. Interestingly enough, the tool that we use to determine if the regression line, the line of best fit, the Y predicted equals A plus BX equation, if that tool works well, we use something that we've already learned this term, which is ANOVA. And so we have to go back to what we know about the sum of squares principle, right? And we talked about how the sum of squares total is equal to the amount of variance we can explain by our X predictor for Y, and the amount of sum of squares total that we cannot explain from the model, which is represented as error, or another term for error would be residuals. And so the total variability represents sum of squares total. We've learned how to calculate that from week 2 of the academic term. And so SSM in this particular case is going to tell us the amount of variability in the regression line data that can be explained by the line of best fit, meaning the predictors that are used to generate that line. And sum of squares residual, or SSR, represents the error of how much cannot be estimated from those predictors. And so we're going to use our tool sets here and how we understand the concepts of ANOVA in order to rule in that line as a line that is good at predicting the Y outcome variable of interest, or one that's not good at predicting it. And so we'll talk a little bit about that. So to test the line of best fit, we're going to use analysis of the variance, right? And because, as we talked about from the previous slide, the sum of squares total can be partitioned or explained by the amount of total variability that is directly attributable to that line and those predictors that generate that line, and the amount that cannot be estimated from those predictors. And so part of what we need to think about is what's known as mean square error, right? And so we need to be able to take it from sum of squares total. And we talked about how we like to use and reference things in terms of mean squares or average squares. So how do we calculate that? We take the sum of squares total values, or the sum of squares for the model, and we divide it by its degrees of freedom. Similarly, for the sum of squares residual volume, you take it divided by its degrees of freedom to get mean square residuals. And then, just like we calculated the F statistic in ANOVA for comparison testing, you take the mean square for the model divided by the mean square for the residual, and you get your F statistic, which can then be calculated and compared to an F critical value to tell you definitively if that line of best fit is a good line at predicting the unknown outcome variable of interest. And so when we calculate these mean squares, we are ultimately trying to generate an F statistic that we can then use to compare to a critical value and determine with 95% confidence if that is a statistically significant line, better than just giving an unknown Y value of interest, the Y average. And so the last thing then that we need to think about before we walk through the process of how to compute the line of best fit and actually do this is we need to determine what's known as an effect size statistic, right? So we talked about effect sizes as it's not tied directly to the sample size. It's simply measuring the magnitude of the effect of a particular finding. And so when we look at the R squared value for the model, this is telling us the amount of variability in the Y outcome or the Y criterion variable that is directly accounted for by the X predictor. And so it tells us how much variability in Y, how much of what I see in Y is explained by X. But remember, this is a correlational type of design, and so it does not infer causality. So that also means while a certain percentage of Y is explained by X, a certain percentage of X is also explained by Y in this kind of a model. And so R squared is simply going to be calculated by calculating the sum of squares for the model and dividing it by the sum of squares total, which, by the way, if you simply take a Pearson product moment correlation coefficient, Pearson's R, and you multiply it by itself, you will get R squared, which ends up being the exact same thing for bivariate regression.